Okay, good morning everyone. So welcome to the first session of the last day on advanced PKE. So the first talk is by Subrana El Dutta and it's multi-client attribute-based and bounded inner product functional encryption and more. Please go ahead.
Thank you. Thank you for the introduction. So myself Subranil. This is joint work with Katrina, Jenith and Tapas. Okay. Functional encryption was introduced by Bonnet et al., where a trusted authority generates master public and master secret key. And in key generation phase, a secret keys are generated corresponding to a key component K, and the ciphertext are generated for a message M. And in the decryption phase, it outputs the functional value f of M and K. The security ensures that no information about the message N will reveal from the functional value f of M and K. Let's see some variants of FE in multiple user setting. In the first variant is called multi-input FE, where the ciphertext are distributed among multiple users, where the secret key is fixed. And if additional labels are embedded in each ciphertext, and the decryption if occurs if all the labels are same, then it is called multi-client FE. And in the next variant, if the ciphertext is fixed and secret keys are distributed among multiple authorities, then it is called multi-authority FE. And if both the ciphertext and secret keys are distributed, then it is decentralized multi-client FE. And its another version is dynamic decentralized FE, which the dynamic condition ensures that any users can join or leave the system at any instant. Okay. So far, various function classes has been studied in multi-users FE setting, such as linear functionality, where the data and functions both are in the form of vectors, and the decryption outputs the sum of the inner product. And in quadratic functionalities, the output will be the sum of the quadrants, and in attribute-weighted sum functionalities, the sum will be the attribute-weighted. And in this paper, we generally talk about the linear functionalities. Okay, let's consider an application scenarios of linear functionalities in multi-user setting, where the goal is to compute the average blood pressures of the patients treated in different hospitals. In this slide, we consider the 3 hospitals, and the blood pressure measurement we embed into the vectors x's. And users obtain a secret key corresponding to an weight vector yi's, where these yi's might represent the importance of the certain measurements of and the confidence levels depending on the hospital practices. Therefore, the functionalities allows to compute the average blood pressures as the sum of the inner product. Okay, now let's consider little bit complex but natural scenarios where the goal not only compute the average blood pressures, also compute the average body temperature. It might be happen that some users is assigned to compute average blood pressures and some users are assigned to compute average body temperature. So considering the efficiency of the system, we can embed both these measurements into a single vector x's, where the odd indices might represent the blood pressures and the even indices of this x's could be represent the body temperatures, and generates the ciphertext corresponding to this new updated xi and upload it into the cloud. Now the users of in order to compute the average blood pressures, now the users obtain the weight vectors for a particular specific form, where the indices of each yi's should corresponds to the indices of the xi's, where the blood pressures are stored. The existing multi-users FEs does not capture this kind of index-specific computations. Also, it might be happen that a new patient join the hospital, then the whole length of this x's and yi's might be changed. So the system parameter should not depend on this length. Yeah, the existing work we cannot capture this kind of scenarios. So if you use the existing multi-users FEs in this context, then when a new patient join, the whole system should rerun from very beginning, which is not a desirable solution. So additionally, for more fine-grained access control, each user size might correspond to an attribute, and the data is only used if specific policies are satisfied. In this example of this average blood pressure computations, the attribute can be the locations of the hospital where it is situated, and the policies P here filters the data. The existing multi-users FE does not capture such application scenarios. So before diving to the solution, let's see some existing work in this context. And there are several inner product functional encryption in multi-user setting. The first MC IPFE with access control was proposed by NPP 22, but they consider the input and functions both bounded length. Later, ATY 23 proposed several multi-users FEs for AWS functionalities where they consider the unbounded length input, but the function still bounded. Although the index-specific computation cannot be captured by these functionalities also. In this work, we propose several multi-users unbounded FEs which captured the application scenario that I discussed in few slides back. In particular, we define and construct multi-client and multi-input attribute-based unbounded IPFEs with n number of parties and having both the input and functions bounded length, and the access control is realized by LSSS access structure. And the multi-client attribute-based unbounded IPFE has one-time level security with selective corruption under the standard MDDH assumption. Additionally, we define and construct dynamic decentralized unbounded IPFEs where the dynamic condition ensures that any user can join or leave the system at any instant of the time, and the security relies on the standard MDDS assumption. Here we consider the unboundedness in more desirable permissive setting, which allows these index-specific computations. In the next slide, I will talk a little bit about this permissiveness. Okay, it looks more complex, but this is the functionalities we consider in our paper. Here the permissiveness actually offers the successful decryption if the index set of the function vector yk is subset the index set of the message vector xk. Okay, now in the technical step, we started with the bounded slotted IPFE of LL20, and then we construct extended slotted unbounded IPFE using the technique of TT18, where we get the unboundedness feature, and then we utilize NPP 22 and construct the attribute-based slotted unbounded IPFE, where we add the access control feature on top of unboundedness. And lastly, we utilize the ATY 23 framework to extend single to multi-client extension. Okay, now just recall the syntax of the slotted IPFE of LL20. It is an hybrid of public key and private key IPFEs where the master public key is used to encrypt the public slot and master secret key is used to encrypt both the public and private slots. And the secret keys are generated corresponding to a key vector y, which have both public and private slot. The slot mode correctness ensures that both the encryptions is computationally indistinguishable, having the private slot equals to 0 vector. And in the function hiding security, the adversary cannot find the challenge bit beta having both the inner product is equal with respect to the challenge messages and challenge vector pairs. Okay, now we can realize the TT18 UIPFE from slotted IPFEs. To construct this, we use 4 slots, where the first 2 slots for the index encoding and the next slot for the key components, and the last slot is actually a secret sharing of 0 depending on the index set of the Y vectors. We use the same strategy to encode the message X into the ciphertext, and in decryption, if permissive relation satisfies, that means the index set of Y vector is subset the index set of the X vector, then it outputs the inner product. So now we use this technique to construct our extended slotted unbounded IPFEs. To compute the secret keys and ciphertext components, we use the first 4 slot for the unboundedness purpose, which is actually similar as the TT18 framework, and next we extend one bounded public slot and one bounded private slot. And if the permissive relations holds, then it outputs the required inner product with some extended computation between the bounded public slots and private slots. Now we use this extended slotted unbounded IPFE as a building block to construct our attribute-based slotted unbounded IPFEs. Here before going to the construction, let's recall the access structure LSSS first, where we first sample A0s randomly, and depending on the access structure, all the edges can be generated. And if the access structures satisfies the attribute set, then the reconstruction will be possible and have these inclusions. Now, using one bounded slotted IPFE and one extended slotted unbounded IPFE, we generate the secret keys as ciphertext components. Here, the bounded slotted IPFE is actually dedicated for the access control part, and the extended slotted unbounded IPFE will handle the both functionality as well as the unboundedness. And if the access structure satisfies the attribute set and the permissive relation also holds, then it outputs the required inner product with some extended computations. Now we use this ABS UIPFE to construct our final goal multi-client attribute-based unbounded IPFE. So before going to the construction, let's recall the functionality once more, where the ciphertext are distributed among multiple users, and each ciphertext are associated with message vectors, some attribute set, and a label. And the secret keys are generated corresponding to an access structures and a collection of all these key vectors. Now we use the attribute-based slotted unbounded IPFE to construct this MCABU IPFE. And in the key generation and the ciphertext generation also, here we can see this YK and XK are the unbounded length, and we use this SK is actually a secret sharing of 0 depending on this label. Now, if the access structure satisfies all the attribute set, then it outputs the required inner product using the decryption of the underlying ABS UIPFEs. So till now we discuss this path where we start with a slotted IPFE and finally we get a multi-client attribute-based unbounded IPFEs. And additionally, we design dynamic decentralized unbounded IPFEs from ATUI technique, and also multi-input attribute-based unbounded IPFEs from attribute-based slotted unbounded IPFEs using the technique of ATY23 and LL20. And for the full entire constructions and security, you can check out our full version. And in conclusion, we formalize the notion of the unboundedness in multi-client attribute-based unbounded IPFEs, multi-input attribute-based unbounded IPFEs, and dynamic decentralized unbounded IPFEs. Realize the access control via LSSS access structure in multi-client attribute-based unbounded IPFE and multi-input attribute-based unbounded IPFE, and a generic compiler from bounded slotted IPFE to a multi-client attribute-based unbounded IPFEs. And in future, we can think about to upgrade the security of the multi-client attribute-based unbounded IPFE from one-time level to multi-level scenarios, and also adding the access control feature on top of the unboundedness in the dynamic decentralized version could be another open problem. So thank you.
Are there any questions?
I guess it's a bit of a general question, but I was wondering what is your feeling about how feasible is the attribute-based version of multi-client FE with like actual labels, not one-time labels, because I feel like this is open for quite some time.
Yeah, exactly. But here the that labels is one time. That means the for all the LOR query, whatever you know that in the challenge query phase, the labels will be the same. This is the restrictions. And now, if we can do this thing, that means the multi-labels also can be preserved. Then also from there we can also develop this dynamic decentralized version, I think. Yeah. Thank you.
Anyone else? So can you give a feeling for like how far away is this from being practical, like in the hospital setting that you used to motivate it?
Sorry?
Is this practical, like in a setting like with this hospital thing, like efficient enough?
Yeah, this is an just normal application. That means where because in the hospital there are several patients, so how can we do this thing? Because also we actually motivate on the unboundedness features, because if you want to find out any statistics and this kind of hospital scenarios, generally the total length is varied.
But could we implement it today, do you think?
Oh, no, sorry.
That's what I thought. All right. Let's thank the speaker once again.
Okay, thank you.
So just a quick reminder that I will ask everyone to please find a chair and leave the stairs open for passage. Can you? All right. The next speaker is Robert Schadlich, and he will be talking about multi-client attribute-based and predicate encryption revisited. Please go ahead.
Hi everyone. Yeah, so this is a work on new constructions for multi-client attribute-based encryption, realizing policy classes that were unknown before. And so the introduction is a bit similar to the last talk. It's basically a special case, but I will recall it anyway to fix the notations. So in the plain ABE setting with one encryptor, we can use a master public key to encrypt a message mu with respect to some attribute x, and we have a key generator that uses the corresponding master secret key to generate decryption keys with respect to some policy f. And as usual, we can decrypt if the attribute of the ciphertext satisfies the policy of the key. Otherwise, we are not supposed to learn anything about the message. And in particular, even having multiple decryption keys, as long as not a single one can already decrypt, having multiple does not help. And to be a bit more precise, when I say attribute-based encryption, I mean that, of course, the message mu must be hidden, but the attribute x can be public, whereas for predicate encryption, we also require that the attribute x must be hidden, and the policy can always be public. Now, a generalization of this model is called multi-input attribute-based encryption. Here we have n encryption slots, and for each slot we encrypt a message mu I with respect to some attribute xi. And correspondingly, policies also have arity n, and we can decrypt a tuple of ciphertexts, one for each slot, if the tuple of the corresponding attributes satisfy the arity n policy. In this case, we can learn all the messages, and otherwise we are not supposed to learn a single message. And importantly, here all the encryptors use the master secret key, which basically means that even though we have several encryption slots and we can, for example, encrypt in different locations, it must basically be the same party that does all the encryption. And to make this a bit more practical, in this work we consider a generalization called multi-client attribute-based encryption. And here we separate the encryption keys and give a different encryption key to each client, and this allows us to consider security in a stronger model where we can consider the case that some of the encryption keys are known to the adversary. This is called corruption. And the second new feature is that now encryption also proceeds with respect to a label, and decryption is only possible if all the ciphertexts that we want to decrypt together, they must share the same label, otherwise we do not learn anything. And this may seem a bit redundant because we already have attributes that specify if we are permitted to decrypt or not. The reason why we still add it here is that in the literature, there are a bunch of policy classes that themselves are not powerful enough to perform such a global equality check to check if all the labels are the same, and to make sure that we always have this feature, we explicitly included in the syntax here. Yes, and so one more detail for the constructions. It is actually sufficient to consider a simpler syntax where only the first client takes a message mu and all the other clients only encrypt an attribute. Why is this sufficient? So given such a one message scheme, we can run n instances in parallel with rotated slots, where in each instance one of the n encryptors takes the role of the first client and can encrypt a message. And in this way, we can generically upgrade from a one message scheme to an n message scheme. This will just make our lives a bit easier when we try to construct such schemes. Okay, so now for the contributions of this work. We give two new constructions for two different classes of policies. The first policy class that we consider in this work are so-called conjunction policies, and a arity n policy is called a conjunction if we can decompose it into n single policies where each fi only takes xi as an input. And with respect to multi-client ABE, this basically means that we evaluate one policy locally in each slot, and globally we only check that all of them are satisfied, but there is no strong interaction between the attributes from different slots, so naturally these policies are much easier to achieve. And so previously in the literature there were two constructions in the multi-input setting. One construction from MDDH for NC1, or arithmetic branching programs to be more precise, and we had an LWE-based construction for bounded depth circuits. Both of these constructions already have security against corruptions, so the only missing feature that we had to add are the labels. But here we can note that such a conjunction policy is not powerful enough to perform a global equality check by itself, so we actually have to work a bit to add these labels. We cannot simply include this label check in the policy. And the second new feature that we have here is about the security model for the lattice-based construction. This previous paper from Eurocrypt 23 did not provide security against collusions, meaning for the entire lifetime of the scheme, the key generator could only provide a single secret key, which of course is a serious limitation. And in this work, we somewhat improve on this by essentially allowing for any polynomial number of collusions. However, this collusion bound must be fixed up front. So we have bounded collusions, and we still have, so we leave open the problem to achieve unbounded collusions. And in addition, one may consider attribute hiding. And there was a work in TCC last year that allows to generically upgrade from the multi-client ABE to the multi-client predicate encryption setting. However, the limitation of that compiler is that it only works for constant arity. Whereas our non-attribute hiding schemes allow for a polynomial number of slots. Here we only have a constant number. Okay, and so our second construction considers global policies, whereby global policies I basically mean everything that cannot be viewed as a conjunction. And here the existing works can roughly be categorized in two groups. The first group considers very strong policy classes like a global NC1 or even global P or bounded depth circuits. However, these constructions all use very strong assumptions, knowledge type assumptions, for example, koala on pairings or private coinevasive RWE. And moreover, the security models that these constructions provide are a bit limited because they don't consider corruptions and they don't consider labels, so they only capture the multi-input setting. And then we have another work from TCC last year where the authors approach the problem a bit from the opposite direction, I would say. Here they say, okay, we want to have a construction from standard assumptions. We want to have a practical security model that supports corruptions and labels. And now let's see which policy classes we can get that are not a conjunction. And so they come up with a few specific policy classes, most notably maybe NC0. And in this work, we kind of revisit this construction and try to improve it. The first thing that we do is, so the presentation of the construction in the TCC paper was that we somehow had these ad hoc function classes and magically the construction worked. And what we try to do in this work is to identify an abstract criterion that is sufficient to make this construction work. We call this new criterion succinct enumerability. And by identifying this abstract criterion, we also find a few more powerful policy classes that were not captured by the TCC paper. And moreover, the construction in the TCC work used pairings, and in this work we also give a pairing-based construction from MDDH, but additionally we provide a lattice-based construction that is proven secure under public coinevasive RWE. And as before, we can add attribute hiding in a generic way if we are okay with a constant number of slots. Now, my remaining time I would like to use to give a high-level overview over the constructions. And so I will start with the construction for succinctly enumerable policy classes. And our starting point is a well-known framework to construct single-client KBABE that combines pairing-based IPFE, pairing-based because we need function hiding security, and we use this together with linear secret sharing schemes. Alternatively, to have a setup in the lattice-based setting, there was a paper in Eurocrypt last year where the authors present a new IPFE primitive called evasive IPFE that is proven secure under public coinevasive RWE. And this one can even deal with stronger secret sharing schemes called noisy linear gobblings. And for the scope of this talk, I will present the construction in this left setup because notations are a bit simpler, we have no error terms, etc. But the exact same ideas can also work in this lattice-based setting. Now, how does this framework work? The basic idea is to start with a linear secret sharing scheme and to view it as I would say, a weak one-time secure ABE. And then we want to use the power of IPFE to re-randomize the secret sharing scheme to obtain full-fledged IPFE security. In a bit more detail, if we want to generate a decryption key for some policy F, we sample some new and secret S, and we secret share it to obtain secret shares, and we place them in the IPFE decryption keys of different instances. And correspondingly, if we want to encrypt with respect to some attribute X, we also sample a fresh encryption randomness R, and we provide IPFE ciphertexts of those IPFE instances that correspond to the attribute under which we want to encrypt. And then IPFE decryption gives randomized versions of these secret shares, all multiplied with the same random scalar R, and now basically we can evoke some DDH style assumption to argue that this looks like a freshly generated linear secret sharing scheme, and then we can rely on the one-time security of the secret sharing scheme to argue that the construction is secure. And the big question here is, how do we distribute this? Because the problem is that all of these IPFE schemes, they depend on XIs, the attributes that are given to different slots in the MCABE model, but they all encrypt the same randomness R. And it is not clear how we can get this shared randomness. And so indeed, in the current work, I would say we don't even try. We let the first client do all the work. Nevertheless, we want the other clients to control which of these IPFE ciphertexts for indices 2 to n can be learned by the decryptor. And for this, we add a second layer of encryption. To be more precise, we use identity-based encryption, where the identities are basically the attributes under which we want to encrypt, together with the labels, but this is not too important here. And then the other clients, they have the master secret keys of the IB instances, so they can generate decryption keys for certain identities, where the identities are the attributes under which we want to encrypt. And so by providing these identity-based secret keys, the other clients can control which of these IPFE ciphertexts are revealed to the encryptor, and in this way we give back the control to the other clients, even though all the IPFE ciphertexts are generated by the first client. Now this partially solves the problem, because now the first client can sample this randomness R and put it in the IPFE ciphertext, but we still have the problem that these attributes here, x2 to xn, they are not known to the first client, so it's still unclear how these ciphertexts here can be generated. And there is no simple solution to this. Basically, what the first client needs to do is consider all possible variants. Like we need to consider all possible variants of attributes x2 to xn and give independent ciphertext for all of them. Now, obviously, if we have a polynomial number of such attributes, then this set grows exponentially and the whole construction becomes inefficient. And indeed, we can't handle this for general policy classes, but we can identify a few particular policy classes where we can keep the size of this set polynomial. And maybe the most natural example are NC0 policies, because they have the nice properties that they are local, meaning even though we have a polynomial number of inputs, only a constant size subset actually matters for the output. And this is great for us because it means that we do not have to consider all possible variants here, but it suffices to consider constant size subsets. And now we can use a simple combinatorial argument where we say, okay, we have a polynomial number of attributes, but the number of constant size subsets is still polynomial. And for a constant size set, we can try all possible variants because 2 to the constant is still a constant. So all in all, we can conclude that for NC0 policies, we do not need all of them, but a polynomial size subset suffices to always find a matching element in the set that allows us to decrypt, which coincides with our attribute vector on the relevant position and actually decide if our policy is authorized for decryption or not. And investigating this construction a bit more, we can generalize this a bit. One example is that the first client actually sees x1, so all these combinatorial things only apply to the second to last element, the second to last attribute, which means that we can actually have an arbitrary bit dependency on x1, and only for x2 to xn we need to require a constant bit dependency. And we can find further examples, all of them being basically instances of what we call a succinctly enumerable policy class. And to hint at this definition very, very briefly, basically what we want to say is that we need a succinct, meaning poly-size set, where for each authorized attribute vector, we need to find a corresponding v in the set that coincides on the relevant positions that decide if a policy is authorized, and conversely for the not authorized attribute vectors, we shouldn't find such a corresponding element. And the way we do it is that this set, we define it to be vectors of bit strings over 0, 1, and star, where star is basically a wildcard that says the position does not matter. And then we want, for each authorized x, we want an element in this succinct set v that coincides on the 0 and 1 positions, and for the star positions we can put any bit. Okay, so let me conclude. In this work, we present two new constructions, one for conjunction policies and one for succinctly enumerable policy classes. And for both constructions, we have an instantiation from MDDH on pairings and one from lattices. Thank you very much. And in case there's a question, I'm happy to answer.
So, are there any questions from the audience? Okay, so I'll ask you a question. So, can you give me an intuition for how you define security? And in particular, I'm interested in like the corruptions part. Is it like adaptive or?
So in this work, we only consider selective corruptions. I think almost all of the multi-client ABE and FE constructions only consider selective corruptions where the corrupted slots need to be defined up front. I'm only aware of one single paper from Asia Crypt 19 for inner product functionality, not for ABE, where the authors consider adaptive corruptions, but yeah, I guess the vast majority is only selective.
Sounds like there's interesting work to do there. All right, any questions? Then let's thank Robert again. Hello. Do you have the microphone? Okay, the next talk will be held by Anhui Lim, and he will be talking about bootstrapping with RMFE for fully homomorphic encryption. Please go ahead.
Thank you for the introduction. So, good morning, everyone. This is a joint work with my colleagues at A-Star and NTU, Kin Mimi Ong, Junjie Sim, Benjamin Hongming Tan, and Hua Xiong Wang. So I'd just like to go through some preliminaries first. The first ingredient that we'll need is something called Galois rings. So broadly, you can think of them as generalizations of finite fields to a prime power characteristic. So they are constructed in a very similar way to finite fields. Basically, you just take your polynomials over zp to the r, and then you take the quotient by some monic irreducible polynomial. And if the degree of the polynomial is d, then we write this Galois ring as gr p to the r for the characteristic and d for the extension degree. And so Galois rings have a very familiar structure to finite fields. So they have a tower structure, meaning that if I have a Galois ring with degree s, then it is a subring of a larger Galois ring that has a degree that is a multiple of s. And in this case, if D is S times W, then we say that W is the relative extension degree between the smaller ring and the larger ring. Then we also have a Frobenius automorphism that fixes the ground ring Zp to the R. But unlike finite fields, we actually have some extra operations. We can define a modular reduction by powers of P. And if we have multiples of P in the Galois ring, we can then define a division by P. So the second ingredient that we'll need is reverse multiplication friendly embeddings, or RMFEs for short. So if we just define a tower of Galois rings G and an extension ring G prime, then an RMFE is a pair of linear maps, phi and psi, that have the following functionality. So phi is able to take vectors over the lower ring G, and we can map it to an element in G prime, such that if I do a multiplication of two outputs of phi in the ring G prime, then I can use psi to recover the component-wise multiplication of the original vectors over G. So there's actually no true homomorphism between G to the K and G prime. So the reason why we can do this is because these two maps actually only preserve a finite number of multiplications. And if you'd like to do more multiplications than is supported by this map, then you'll need to evaluate whatever is here by something called a recode map. Basically, you just decode it and then you re-encode it again. So with these two ingredients, finally we reach homomorphic encryption, which is basically an encryption scheme that enables computation on a ciphertext without decrypting to the underlying data. So here we have the classic preservation of addition and multiplication. And in particular, in this work, we'll be focusing on the BGV and the BFV schemes, which technically enable Galois ring arithmetic, but they are usually just used for arithmetic over Zp to the R. Now, when we do ciphertext multiplication in these two schemes, or actually in every scheme, you end up accumulating a lot of ciphertext noise. And it is possible that if you do too many multiplications, the noise will eventually overwhelm the message. So in order to prevent this and to bring the noise in the ciphertext down, we need a algorithm. We need a protocol called bootstrapping that helps to bring the noise in the ciphertext down, and that allows us to then continue doing more multiplications. So this current work is built on top of a previous work in 2022 called Field Instruction Multiple Data. So ordinarily in BGV and BFV, you have a data vector over Galois rings. Each of the components are just called the HE slots. And this data vector is packed into a plaintext polynomial using the Chinese remainder theorem. And the plaintext polynomial lives in this, an example like this ring. Then this plaintext is then encrypted into the ciphertext that we then do encrypted computations on. And so in the 2022 work, they introduced a second layer of packing using RMFEs, so that now we have RMFEs over, we have data over a lower Galois ring. We can pack this into a Galois ring extension element, and then this is then packed into the plaintext polynomial. And so then addition and multiplication on the ciphertext is carried over to the plaintext, is carried down component-wise to the HE slots by the Chinese remainder theorem, and then they are carried down further component-wise to the RMFE slots by the preservation property. So in this work, we try to tackle the question of how do we then bootstrap an RMFE-packed ciphertext. And in particular, we explored trying to emulate the thin bootstrapping pipeline, which is an optimization of bootstrapping, but it only works when you have integers in the HE slots. So basically, you've restricted yourself to just putting integers here. And so the thin bootstrapping pipeline can be broadly divided into two phases. We have a fast linear phase and a slow digit extraction phase. And so the dream is to somehow adapt this pipeline to work for an RMFE-packed ciphertext. And in particular, in our work, we targeted trying to adapt this digit extraction portion to work when you have RMFE packed Galois ring elements in your HE slots. And so we managed to do this. So the main technical achievement of our paper is the following. So before, in ordinary digit extraction, you have an integer here represented by its highest to lowest digit. And then digit extraction will just output the lowest, I'll just output the highest digit. And so in our work, what we could do is now we have many integers here represented by their digits. You can use the RMFE encoding map 5 to encode it into a Galois ring element. We put this through digit extraction, and from your output, you can then recover the desired highest digits. So to just give a very, very rough impression of the kind of modifications that we made. So here we just have normal digit extraction. This is the Halevi and Shoup design of digit extraction. So it looks a bit scary, but the main takeaway is that, so you have input integer z. We have to do many, many evaluations of a special lifting polynomial. And we also have to compute some intermediate terms here that I've shown here. So I've color-coded it so that you can see which evaluations of the polynomial are used for which term along the diagonal. And so the important thing to note is that when you are computing these intermediate terms, the numerators here are always guaranteed to be multiples of p, which is how we can then do division. But this is only guaranteed when your input is an integer. So you can imagine that if we replace this with a Galois ring element, we suddenly don't necessarily have that the numerators are divisible by p. So then we need to try and fix this somehow. So the naive, straightforward way is we can just say, we can just recode. We can just call the RMFE recode function after every time we do one of these polynomial evaluations. And we show in our paper that indeed, if you do this, then your numerators are back to being divisible by p. But the problem with doing this is that you're doing many, many linear map evaluations, and in practice, evaluating the recode map homomorphically is very expensive, both in time and in noise building. And so we proposed an alternative, which is using something that we call correction maps. So basically what these maps do is they sort of do a change of basis on the image of your encode map. Basically you take your canonical basis of the image of phi, and then we map it to just the exponentiation of the same element, but to the power of p to the I, where I is a parameter that we set. And so if you do this, we can see that now we are back to just doing polynomial evaluations. There is no evaluation of the recode map in this part of the triangle. And we only have to do just one recode at the end here. So where do these maps appear is basically they are the first terms in the computation of the intermediate terms and the result. And we give an inductive proof that indeed, when you use these maps in this way, that we can always obtain a multiple of p, and we can then do the iterative division by p that we desire. So in our paper, we managed to implement the following pipeline. So unfortunately, we didn't manage to do just one linear phase. We have to kind of split the ciphertext into multiple linear phases, but we can just do one round of digit extraction, RMFE digit extraction. And so we implemented 4 different bootstrapping workflows in C++ with the HElib library. And they are divided as follows. So we tried 2 different RMFE. So we tried RMFE bootstrapping with 2 digit extraction strategies. The first was the naive way that I showed before, where you just do many, many recodes throughout the algorithm. This actually gives us the best ciphertext packing, but it usually results in a impractically low number of multiplications after the bootstrapping procedure, and it usually has a very high execution time. Then we also implemented the correction map technique that we showed before, and it yields more multiplications after bootstrapping because you're not doing as many you're not doing as many linear map evaluations, and also has a lower latency because correction maps are very, very easy to evaluate. But the problem is that it doesn't have quite as good packing as the naive way of doing it. And so for each of these two styles, we also tried two different optimizations of the recode map. The first is just using a standard baby step, giant step optimization that is well known in FHE. So normally when you are evaluating the recode map, it takes about W many automorphisms, where W is the relative extension between your lower Galois ring and your higher Galois ring. So the baby step giant step gives us 2 square root W many automorphisms, and we also introduced a new kind of optimization called trace and merge that gives us K, which is the length of the RMFE vector, times log of W many automorphisms. So here are just some sample results. So you can see that when we use the naive way, indeed we can get a lot of slots, 342 for p equals 3, 206 for p equals to 5. But the remaining capacity after bootstrapping is very, very low. And this translates to maybe only being able to do 2 rounds of ciphertext squarings before your noise overwhelms your ciphertext again. And the latencies are very high, they're in the hundreds. And if we change then from the naive technique to the correction map technique, then the amount of capacity that we have left in the ciphertext increases. And that also translates to being able to do more ciphertext multiplications, and we also bring the latency down by more than 10 times. But unfortunately, the number of slots that you'll get is lower than the naive way of doing it. And you can also see that when we do the trace and merge, we get a slight trade-off in latency and in capacity. But unfortunately, if you look at if we use the holistic throughput metric, we can see that actually just using normal thin bootstrapping technically gives us the best holistic performance. So these techniques are still not competitive with the state of the art, but we wanted to show that our correction map technique does kind of find the middle, does kind of give an improvement from just doing everything naively. And it's also an encouraging result that maybe we can maybe somehow improve over this over time. So to reiterate again, this current work is foundational. It's not yet competitive with the state of the art. And so for future work, we could try some things. We can try a sort of a hybrid style that uses both the correction map technique and also maybe just doing a bit more recoding. Then we can also look at trying to just do one linear phase instead of multiple, which we had to do in our work. And lastly, we can also think about trying to extend the correction map strategy to more recent digital extraction algorithms by those by Chen and Han in 2018, and the more recent Gielen, Ilyashenko, Kang, Vercauteren optimizations in 2023. So these are my references, and thank you for your attention.
Any questions from the audience? We have a little time for questions yet. So where do you see this going, essentially? Do you think that you will be able to compete with the state of the art eventually?
So kind of an open question, but I am somewhat optimistic because especially because this recode function, which is currently the main bottleneck, these two optimizations are actually they're not very sophisticated optimizations. We have reason to believe that we can in fact bring this down to maybe just log W, which will help to speed things up a bit. Also because this only This technique is only so far investigated for the Halevi and Shoup design of digital extraction. So we're still not entirely sure whether we can get even better optimizations if we applied it to the current state of the art. Then maybe there's a room for improvement there. Yeah.
Right, interesting. Well, let's thank the speaker once again.
Thank you.
Okay, so then we're ready for the last talk of this session. This is from Anna Maria Kustache, and she will be talking about revisiting the security of approximate FHE with noise flooding countermeasures. Please go ahead.
Thank you very much. Yes, so I'll be presenting this today. Thank you for the introduction, and this is joint work with Flavio Bergamaschi, Dana Dachman-Solid, Hunter Kippen, Luca Leboeuf, and Ray Tang. Flavio's at Intel, Dana, Luca, and Ray are at UMD, and then Hunter is at Samsung. Okay. So let me start by introducing FHE a little bit. So we had a brief introduction before, and I'm sure most people have heard of it, but I'll spend a little bit of time on this. So homomorphic encryption is a type of encryption that allows you to compute unencrypted data, right? So you can do a lot of things with it, but it's easier to illustrate with outsourced computation. So you can think of, you have a client who has some data, M, and she wants to evaluate some function F on the data M, but she can't do that herself, either for resources reasons, or the computation can be like intellectual property, right? So what she can do is that she can encrypt the data M, send that along to the server, and then homomorphic encryption works in such a way that the server can apply the function F to the encrypted data, and then that results in an encryption of F of M, and then the server can just send that result back to the client, who can then decrypt and recover F of M in plain text, and then of course all the while the server hasn't actually gotten access to either M or F of M in the clear. So I'm gonna particularly focus on one scheme, which is CKKS, which was introduced at AsiaCrypt in 2017. And so one feature of this scheme is that it's an approximate FHE scheme. So what this means in particular is that even for a fresh encryption, so by fresh I just mean an encryption that I haven't performed any homomorphic computations on, so even for that, if I just take a message, I encrypt it, and then I immediately decrypt it, so again, no homomorphic computations, then I actually recover M plus E, where E is some noise. So I never recover E exactly in the scheme, and it's a very nice scheme because it allows allowed the authors to actually get a lot of efficiency improvements, and sort of the main thinking behind this in this paper was to think, well, actually in a lot of sort of like real world applications, you actually only need approximate results, right? So you can sort of get away with not having exact results. Which was very nice, except that in 2021 at Eurocrypt, Lee and Michancho actually showed that this approximate correctness feature can actually lead to efficient key recovery attacks. And sort of the reason for this is that this noise, this sort of noise is has some information about the secret, about the sort of error secret LW vector. And so in this LM21 paper, the authors captured this sort of insecurity notion, I guess, in this model that's called INCPAD. Okay, and then in a follow-up work a year later at Crypto 22, Lee, Michancho, Schultz, and Sorel propose noise flooding as a countermeasure to the attack that was presented in this Eurocrypt paper. And they actually show that using differential privacy techniques, they can actually prove security. Okay, so this works, and this sort of counters this key recovery attack, except that this actually leads to a very large efficiency loss. So actually to get sort of like provable security, to prove security in this using these differential privacy techniques, you have to use like quite heavy noise flooding. And in particular, the resulting modified scheme loses a lot of message precision bits. Okay, so we kind of go from like having a lot of space for the message to just not having a lot of space for the message. Okay, so then that brings me quite nicely to what we do in this paper, which is the goal of this paper was to investigate the concrete security degradation of the CKKS scheme in the presence of T decryptions with noise flooding of some variance rho squared. So in particular, we sort of consider the optimal setting for this noise flooding, for the variance of the noise flooding to be equal to the noise already present. So then you lose 1 bit of message precision because you're effectively only sort of like doubling the size of the noise. And then on the other side of the spectrum, then you noise flood for provable security, so sort of like noise flooding levels in LMSS 22. And so our aim in particular is to present trade-offs between the number of allowed decryption queries before you have to refresh the keys, then the variance of the noise flooding noise, so in particular how much noise precision you lose, because again, sort of the larger the variance of your noise flooding noise is, then the more message precision you lose. And as well the concrete security of the scheme after a certain number of decryptions have been observed by the adversary. And so to do this, we're going to use this LW with side information framework, which was a framework presented at Crypto 20 by Dana Dahman-Solid, Leo Ducat, Huijin Gong, and Melissa Rossi, which is a framework for cryptanalysis of lattice-based schemes when side information about the secret and or noise is available. And they sort of use the terminology of hints in that paper, and then we're going to use that terminology as well. And so in particular, what this framework allows you to do is that it allows you to progressively integrate hints on the secret error LW vector before running a final lattice reduction step. And so in that work, they propose 4 types of hints. They propose modular, perfect, approximate, and short vector hints, and we're going to use the 2 I've highlighted in this work. So we're going to use perfect hints, meaning you have a perfect inner product between the secret vector, the secret key, and some vector. And we're going to use approximate hints, which is you have the approximate value of the inner product between the secret S and some vector V. Okay. So for the methodology, what we do is that we model the leakage that we have on the noise in CKKS decryption as hints. So in particular, if you're not familiar with the CKKS scheme, then, this is a simplified view, but that's, at a high level, this is what it is. So the decryption of a fresh CKKS ciphertext is going to look like this. So you have the message M, and then you have some product between S and some noise E, to which you're adding some other noise E. Okay, so you can kind of see how this is like an approximate hint, right? And then for ciphertext that you've computed on, it looks a little bit different, but the idea is there. And so what we're going to do is that we're going to investigate noise flooding by rho squared, 100 times rho squared, and T times rho squared, where rho squared is an average case estimate of the variance of the underlying noise as estimated by this SAC 2022 paper. And T is the number of decryption queries. Okay, so again, we're sort of what we're investigating is noise flood by rho squared, which is the noise that's already present, so sort of like optimal setting. We look at an intermediate value, which is 100 times rho squared, and then we look at T times rho squared, where T is the number of decryption queries that the adversary gets to observe. We also validate our results by running estimate for the noise flooding levels suggested in LMSS 22, so for the levels where you can prove security. And then we run all of these attacks for parameters suggested by homomorphicencryption.org. Okay. We also capture our threat model in a new security model that we call NCPA-DSH. So again, remember that the LM21 paper proposed NCPA-D, so we add an SH where the SH stands for semi-honest. where here we aim to capture all semi-honest attackers with access to a restricted decryption oracle. So we restrict the adversary to evaluating circuits on fresh, independent ciphertexts that are each used at most once. We restrict the adversary to certain classes of circuits, and I'll talk a little bit more about that later. We don't allow adaptive queries to the evaluation oracle, so the state is only released to the adversary at the end of the game, because actually we point out that otherwise this allows for adaptive attacks where the adversary can bias the noise distribution. But we also release the encryption randomness to the adversary, of course, whenever this doesn't lead to a trivial distinguishing attack. So in particular, if you're familiar at all with NCPAD, we're actually sort of orthogonal to NCPAD because NCPAD doesn't really restrict the adversary to certain classes of circuits, allows adaptive queries to the eval oracle, but it doesn't release the encryption randomness. So we're sort of, again, a little bit orthogonal. So I mentioned we restrict to certain classes of circuits. So the three types of circuits that we consider here are identity circuits, and then what we call class 1 and class 2 circuits, where again, so the inputs to both of these are fresh independent circuit ciphertext are each used at most once. And really what you should look at here is that here in the class 1 of circuits, here we have a multiplication with a rescale, and then we're adding a bunch of ciphertext. And then here, the final step is a multiplication without a rescale. Okay, sort of essentially here we're gonna consider quadratic hints on the secret key, whereas here we only really consider linear hints on the secret key. Okay. So as I said, the hints consist of noisy linear equations on the LWE secret error vector, where the noise is sampled from a Gaussian distribution. Now, one important difference from this LWE with hints framework that was presented at Crypto 2020 is that they only really considered like LWE-sized parameters. So in particular, for us to sort of be able to use their framework, we need to compute the determinant of a 2n by 2n matrix. That's obtained from T hints for very large values of n. So like for FHE size parameters, n can be somewhere between like 2 to the 11 to 2 to the 17. So it's quite large values of n. So what we do instead is that we compute the expectation of the determinant. So we provide the closed form expression for the determinant, and we also provide experimental validation for this. So that was sorry, I don't think I said this in the beginning. So that's for the lattice attacks that we consider to estimate the security of the resulting CKKS instance. We also consider guessing attacks, where in these, after integrating some T hints, the adversary can then guess n out of 2n coordinates of the LW secret error vector with high probability. And then after it's done this, then it can solve the original LWE system for the remaining n coordinates. So here again, keeping track of the covariance matrix requires a 2n by 2n matrix inversion, which again is not computationally feasible for our parameter sizes. But instead, if we know the distribution of the matrix, then we can get bounds on the trace and the eigenvalues with high probability, and then we can use this to bound the success probability of the guessing attack. So this is the approach that we take. Okay, and then we consider hybrid attacks, which combine the two strategies, where the adversary can guess G coordinates with high probability, but G is smaller than n. And then it integrates those G guesses as perfect hints. So remember I told you we're using approximate hints and perfect hints. This is where the perfect hints come in. Okay, so now I can talk about the results a little bit. So I don't have time. We have, if you're interested in our work, we have a lot of tables and a lot of graphs in the paper, and I don't have time to talk about all of them. So I'm showing you the trends for the hybrid attack. So again, combining the two of them. The lattice and the guessing attack. And so we have the reduction in bit security on the y-axis, so meaning this is like the security loss on the y-axis, and then on the x-axis we have the FHE dimension n. And so what we can see is that for low values of n, then you can have quite a big reduction in bit security, but then actually as n grows here, then this reduction really, really drops. Okay. So some general observations about our results. So as I said, we do validate that there's no security drops in our experiments when using the provably secure noise flooding levels, and indeed we observe that. So when we run the estimator for those levels of noise, then there's no drop in security. We see a greater reduction. We see a greater reduction in bit security for lattice attacks for identity circuits versus class 1 and class 2 circuits. Again, I don't have time to show you the graphs, but if you look at our results, then it's sort of the lattice attacks are much more efficient for identity circuits rather than class 1 and class 2. We also see a greater security reduction for higher target security level versus lower target security level. Although again, sort of as I show you, like the trend is that, as n increases, then this security drop decreases anyway. And then guessing attacks perform significantly better for class 1 and class 2 circuits versus identity circuits. So if you look at the number of hints that you need for identity circuits versus class 1 and class 2, you need a lot more decryption queries for identity circuits for the same success probability of the attack. And then again, as the value of n increases, then the security level drop decreases. Okay. So for the conclusion, so as expected, noise flooding by the lowest level incurs the biggest security drop, so that's not really a surprise, right? So again, remember that the lowest level of noise flooding we consider is the level of the noise that's already present in the ciphertext. Whereas on the other side, sort of noise flooding by t times rho squared, where again t is the number of decryption queries that the adversary gets to see, then actually that leads to a very low reduction in the security level, if at all. So again, you can look in the tables, but if you noise flood by this, then sort of there's very, very low drop in the security level. So we sort of suggest that perhaps a less cautious approach could be to noise flood by alpha times t times rho squared for some alpha between 0 and 1. So you could think of alpha as a fine-tuning parameter. The sort of thinking behind this is that, perhaps for some higher dimensions, like a security drop of a few bits might be acceptable, right? So if you think of deployment, if you go from 256 bits of security to 253, is that really, perhaps that's something that we can live with in implementations. And so I think, this is my last bullet point, but I think something that's important to sort of, we state in the paper, and it's important for me to restate as well, is that, we don't, you shouldn't use the results and the techniques that we have in our paper to sort of take as we don't say this level of noise flooding is okay. Really what we want to give is, trends, and we want to show how things evolve, and how you can, again, sort of view these, this noise in FHE as a hint in LW, and you can use that framework to, derive, some conclusions about the concrete security of the scheme. But then, of course, the final, there's no sort of definite answer to how much noise flooding should you add. It kind of really depends on your application, right? So in particular, one of the things that we suggest is that you could use techniques and results of this work to establish key refreshing policies, right? Again, so you can see after this many decryption queries, I drop 5 bits of security, maybe that's fine, but maybe after this many queries, I drop 30 bits, and maybe that's not so fine anymore. So again, we're not sort of given any definite guidance. We're just showing how the security evolves, and in terms of concrete security, and then for real applications, then you can sort of use the results of this work to establish things like key refreshing policies. Thank you.
Questions? So can you tell me, what are the prospects for proving security of this CPA SHD?
What do you mean?
So when I'm seeing attacks and bit security losses, I'm thinking there should be a matching provable security bound, like concrete security bound. But is this challenging?
I mean, I think so. Like what we're looking at here in this paper is not in the provable security regime, right? So what we're saying is you can get provable security, but that's with very high levels of noise flooding. You know, and if you sort of agree to not have that, and then look at the concrete security drop in terms of like, you know, concrete attacks, what we have. So that's sort of what we look at in, you know, for if you wanted to get provable security, then you would have to noise flood by more than what we sort of do here.
Sure, I was thinking more like whether you could find the same sort of trade-off in like a security bound. That would be interesting. But I guess that's for the future to look at.
Yeah, I guess that's future work. It would be somewhere in between between the two, yeah.
I had another perhaps silly question, which is that since you're already using these differential privacy techniques, is it possible to get like two birds with one stone for applications where you want differential privacy?
Oh, that's a good question. I think there is a paper from RSA in 2023 or 2022 from Tabitha Ogilvy, I hope I'm pronouncing that right, that I think does exactly that. Yeah, where you kind of get like differential privacy for free because you have some, it's sort of using the underlying noise in FHE to get some differential privacy for free, yeah. Yeah, I should add, we don't use differential privacy techniques in this paper at all. This is really just to set sort of the, you know, the limitations of like, this is worst case provable security, this is best case, not, you know, less security.
Makes a lot of sense. There's a question here.
I was just wondering, now that you are adding different amounts of noise, which is more than initially described for the scheme, do you take the hit in message position, or do you take it for like extended parameters and performance, or what's a kind of reasonable way to approach this additional noise?
Yeah, that's a good question. It's a little bit of both. So essentially you are gonna lose something like, you know, log t plus log rho of bits of message precision. And then, you know, the hit and parameters is really gonna depend. So then it's gonna be like a trade-off between, you know, have you lost so much precision that you actually need to bump the parameters up, or, you know, have you maybe lost like 1, 2, 3, 4 bits of message precision out of 50, and then that's still acceptable. But yeah, it could be that you lose so much message precision that you then need to bump the parameters up. Yeah.
Thanks.
Any others? Yep.
You mentioned that you could use noise flooding to get provable security, but you take a loss in performance.
Yeah.
Is this performance relative to precise homomorphic encryption, where you have completely corrected encryption, or just relative to the kind of noisy decryption that's described here?
Yeah, that's a good question. I don't have a good answer for that. Like, I don't know that anyone's done the comparison directly between like noise flooded CKKS and you know, exact FHE scheme. So in the LMSS 22 paper, they end up with like, I think either 8 or 16 bits of message precision for like reasonable parameters. I'm like quoting the paper. And that's versus something like, you know, anywhere between like 30 and 50 bits of message precision that you would have in the non-noise flooded setting. So it really depends, you know, so that's to give you an idea of like how much loss they incur. And then in like BGV or BFV, you know, it kind of really depends on your application, but you could quite easily have like more than 8 or 16 bits of message precision in those exact schemes. Yeah.
Thank you.
Okay, then let's thank Anna Maria and all of the speakers of this session again. So please stick around for a few minutes more as the chairs have something to show us.
Yeah, so we got some video from the author of Test of Time Award. So I think we can spend something like 6 minutes roughly to listen to what the author has said. So the first one is from the paper Signing a Linear Subspace Signatures Schemes for Network Coding.
Hi everyone. We were all super excited when we found out that our paper from PKC 2009 won the Test of Time award. We want to thank the committee, and we are very sorry that we can't be there in person. The paper shows how to sign a linear subspace. At the time, back in 2009, network coding was all the rage. It showed that one can reduce traffic when sending multiple packets through a network. The trick is that nodes in the network compute linear combinations of packets as they traverse the network. We were interested in how to provide data integrity in these settings. To do so, we had to develop the notion of a linearly homomorphic signature scheme. A signature scheme where given two signed vectors, anyone can create a signature on a linear combination of those two vectors. Our 2009 paper develops this concept and presents two such schemes. These ideas later led to more general homomorphic signatures, and finally it culminated in the development of fully homomorphic signatures. Again, thank you for the Test of Time award, and I hope everyone has a wonderful time at PKC 2025. Brent, do you want to say a few words?
Hi, I wanted to say thank you for this very nice Test of the Time award. I'm sorry I wasn't able to be there in person, but I hope to see everyone at a conference in the very near future.
I also just wanted to add my thanks to the committee and my apologies that I can't be there in person to accept the award. I vividly remember working on this paper, and so it's very meaningful to have the work recognized with this Test of Time award. Thank you.
I'm honored to be part of the team receiving the PKC Test of Time award, and I'm very sorry I can't be there at the conference with you to learn about all the latest developments in public key cryptography. Writing this paper back in 2008 was a great learning experience for me personally, and I'm very happy to see that the work has had a long-term impact. So a big thank you to the committee for the honor, to all of you for continuing to carry the research forward, and I hope you enjoy the conference.
So the next one is an accumulator based on bilinear maps and efficient revocation for anonymous credentials.
Hi everyone.
Hi everybody.
Hello everyone.
Thanks so much.
Thanks a lot. Yeah, I mean this was great news for us. We're very happy for this award. It's been a long way. It's been 15 years.
You remember, Claudio, like how this happened, like why you got involved?
Yeah, I was. I mean, this was my first internship during my PhD. It was at IBM 2007, and I started working with you. And the problem of revocation, of balancing privacy and authentication, was really interesting to me. So we started talking about this, and yeah, this was somehow where it sprouted.
Yeah, I guess we were working on this European project. This was the second one. We had like Prime Privacy and Identity Management for Europe. Then this one was Prime Live. We really tried to get this like privacy technology into real world, right? Remember, Marco, like a series of cool projects, cool people.
It's a hard problem. I think we were close to inventing Zcash, I think, as well, and Zero Cash. Like, it's kind of related to all of those things. But of course, we didn't think of blockchains yet. It was before Bitcoin, I think.
Right. Yeah. This was before blockchain, before decentralized identity. So it was really earlier than that. Then those technology came along, and things just fit together all together, right? This was amazing to see.
Yeah, and I guess probably the reason that why this stood the test of time, right? It's still a problem that's not really solved in practice. Because you see, like everybody now, it's different from before. Now people have mobile phones, right? Where actually they could run this kind of algorithms, and Google has now some system where they do proofs of knowledge, like privacy and anonymous authentication. There's the EU new guidelines that people were working on. So actually, I think we might see this technology being used, right? And I guess also these credentials you need to.
And it's actually deployed. It's in Hyperledger Indy. I did a bit of research as a kind of a nice survey of these accumulator schemes, and it's one of the deployed ones. Yeah, I also wanted to say kind of, what's cool about it is there's kind of this update feature. And so I think it has some unique things about it. One interesting thing about research, maybe in terms of advice to new PhD student, is that it gets a lot of citation because it's kind of out there as one of the first 3 kind of efficient accumulator schemes. So whenever someone works on accumulators, we get a citation. So that's nice. Get some of those papers. It's great for your career. So that's positive advice, and maybe a bit of a negative advice. So we worked on accumulators, and we thought accumulators the great big problem. And there's the Nguyen accumulator, which is the first pairing-based accumulator, and it came out already in 2005. And then there's another paper that essentially uses the same techniques, in my opinion. If you look under the hood, which is on polynomial commitments in 2010, and that's now, of course, like has even, I don't know, in the tens of thousands citations probably, because it's used in every SNARK scheme. So so it's kind of important to work on the right problem. Accumulator is a great problem, but SNARKs and polynomial commitments is even better. So it's interesting, and you can't predict really what will happen as well.
Yeah, nobody can predict the future, but if the future turns out getting a test of time award at PKC, that's the best that can happen, right? So thanks a lot, everybody. Sorry, we couldn't make it. I guess part of you already had booked flight, right?
Yeah, I had my flights booked, so I double booked myself. I was so eager to come that I double and triple booked myself, actually. Yeah, I also had a talk today that I had to cancel and move to another time, so yeah.
Yeah. Anyways, thanks a lot, guys. Hope to see you the next conference somewhere. So we could
have a great time in Borås. I was looking forward to the nature, actually. Scotland is nice, but I heard that Norway is the real Scotland. But or the other way around.
Thanks a lot.
Thank you so much.
Bye-bye.
Thank you. Bye-bye. Bye-bye.
So thanks all again. I mean, also thanks the speaker who spent their time to make the video. So now I think the general chair has